To all of you joining me for this video, I am Mr. S. Thank you for watching. Imagine we're taking an exam and we have this specific function provided, x squared over 2 minus x cubed. You have to evaluate this with regards to the derivative tests for the concavities, inflection points, and the relative extremes that might develop. If I'm taking that exam, I'm going to show you the framework that I would follow to answer this in a comprehensive manner, so allow me to show you that. As a very first step, I can look at the roots of that equation. If I were to isolate an x squared, I have a 1 over 2 minus x. When I solve for that x, I get a 0 and a 1 over 2. When I'm looking at that 0, I plug it into your original function. I know I'm getting a 0 comma 0. And when I put 1 over 2 in there, you know what you're getting. You're getting 1 over 2 comma 0 because these represent your x-intercepts, the areas where your y value would be 0. So it makes sense. Now, what I would do next is to determine the first order derivative. You do x squared over 2 minus x cubed and its first order derivative. It's not hard. You get x minus 3x squared. I can do the second order derivative next. The first order derivative will enable me to find the critical points. This will allow me to identify them as being relative minimum or maximum. The second order derivative is 1 minus 6x. When I take this first order derivative and I isolate the x, I have a 1 minus 3x and I make it equal to 0, I get two values. I get a 0 and I get a 1 over 3. These represent the x-axis value of two critical points. When I put 0 back into that original function, I have a 0 comma 0, which happens to be an x-intercept as well, which is fine. Your root can be an extreme. When you put 1 over 3 over here, you get a bit of a convoluted number, but I worked it out on the side for you and I did it here in a fractional form so it looks good, and it's a 1 over 54. Now, I look at the second order derivative to help me decipher the nature of these critical points. When I put everything in terms of these x-axis values in place of this, when I put 0, I get a positive outcome. When I put the 1 over 3, I get a negative outcome. That tells me this 0 comma 0 is a relative minimum, and I'm just going to write that as RMN, relative minimum, and this here with a negative outcome is telling me it's a relative maximum, RMX. Now when I'm looking at those 3 points, because one is a double point, counted twice, one as an x-intercept, one as a relative minimum, I can graph this out. When I graph it out, I have a 0 comma 0, I have a 1 over 2 comma 0, then I have a 1 over 3 comma 1 over 54, which would be a very small number. I have a graph which will very likely come like this, and it'll go in that direction. Now let's talk about the first derivative test. The first derivative test will help me confirm the fact that these local extremes are correctly identified. If I were to draw tangent lines anywhere on this curve, you know in this area your tangent lines would all slope downwards. You'll have a minus, minus, minus. Here you'd end up having a 0. As you pick up on this side, you're seeing positive tangent lines. Remember, first derivative test, you go over that extreme, you start seeing minus. When you're going here from a minus to a positive, you know you're looking at a local minimum, which indeed is a relative minimum. When you're going from a positive to a minus or negative values, you're looking here at a local maximum, which I've identified correctly as my relative maximum. So the first order derivative test helps me verify the fact that I have indeed identified my extremes correctly. And I will put them down over here now on the graph. This here is a local max, LOCAL, local max. Here we have a local minimum. And let's put it right over here. Local minimum, local max. If you were to look at tangent lines over here, you know the function is above your tangent lines, so you're looking here at a concavity which points upward. If you were to draw tangent lines here on this curve, you're looking at a function that's below your tangent line, so you know you have a concavity down. Concavity up, the concave portion is pointing up, the concavity down, the concave portion is downwards. So we know that. Now let's look at the inflection point analysis. We're going to do everything here with regards to the second order derivative. The very quick fix to that, or the quick hint to you, is you know you're looking for a position in your curve somewhere between one extreme to the other extreme right over here, where your positive will change to a 0 to a minus, or based on the signs it's go from minus to 0 to a positive. You're looking at the situation where the second order derivative with regards to the x-axis values you're plugging in, it changes sign. And the best area is to look where that equals 0, because if it equals 0 on either side, there was a sign change. to give you that intermediate 0 value. In this instance, if you're looking at second order derivative and you're just plugging these x-axis values from here 0 up to this 1 over 3. Initially, if you're putting like a value close to a 0, you know you're getting positive signs. If you're putting a value close to 1 or 3, you know you're getting a minus sign. So here in this specific instance, your inflection point somewhere in between is going to have a positive prior to it and a minus prior to it. So we're looking at this specific scenario over here. Anyhow, make this second order derivative equal to 0 and you'll exactly determine your inflection point. 1 minus 6x is equal to 0 and x here is equal to 1 over 6. 1 over 6 here represents your inflection point in terms of your x-axis value, but we need to have a good coordinate pair. So let me convert this x into my IP. My inflection point is 1 over 6 comma. You have to take that 1 over 6 and plug it into your original function. But again, the fractions are quite convoluted because of all those powers, and I worked it out for you over here. It's going to be 1 over 108. 1 divided by 6 comma 1 over 8 is going to represent your inflection point where these positives convert into minus, where your second order derivative changes sign, or where your concavity up changes to a concavity down. Now that we've identified this, let's write the interval for concavity up. My concavity up or concave up is from minus infinity coming up to this x-axis value of your inflection point 1 over 6. My concave down is starting from your x-axis value of your inflection point but going towards infinity. So this right here is my concave up portion, then this right here is my concave down, and there it is. The break in between right over here is your inflection point where that switch occurs, or where your second order derivative changes sign, and everything here has been done for you. The first order derivative test confirmed our local extremes. The second order with regards to these sign changes confirms our inflection point, and it also helps establish the intervals of these concavities which are involved. We have a local minimum, local maximum. The local minimum is one of your roots. Your other root is 102 comma 0, and your local maximum you see right over here. The question has been completed, your intervals are provided, and with that we wrap this video up. Thank you, have a great day, bye.